Hi, my name is Brady and I'll be giving a presentation on the internal combustion engine. So what exactly is an engine? An engine is a device which can transform the chemical energy of a fuel into thermal energy and use this thermal energy to produce mechanical work. Since they use that thermal energy, they are also known as heat engines. Within the concept of heat engines, two different types exist: the internal and the external combustion engine. Since this presentation is over internal combustion engines, I'll just slightly touch on external. The difference between these two types of engines can be pretty straightforward, just by looking at the difference of the names. An external combustion engine uses a working fluid, either a liquid or a gas or possibly both, that is heated by a fuel burned outside the engine. The external combustion chamber is filled with a fuel and air mixture that is ignited to produce a large amount of heat. This heat is then used to heat the internal working fluid either through the engine wall or a heat exchanger. The fluid expands when heated, acting on the mechanism of the engine, producing motion and usable work. A steam engine is an example of an external combustion engine. Some of the advantages of an internal in comparison to an external are a higher output per unit weight, a lower initial cost, they are compact and they require way less space, and they are easier to start up in colder conditions. There are definitely some big disadvantages though, like the fact that the internal combustion requires only liquid or gaseous fuel of a certain specification. These fuels can be harmful to the environment, and they can also be more expensive. Also, the reciprocating parts can become unbalanced due to vibrations. So what exactly is an internal combustion engine? Well, like with the external, the difference is clear when considering the name. An internal combustion engine, such as the gasoline or diesel engine in your car, truck, tractor, etc., uses air as a working fluid. It traps it inside the cylinders and adds heat by burning fuel with it. So post-combustion, your working fluid is now a hot mixture of air and combustion products. To put it even more simply, if you take a high-density energy, such as gasoline, and put it in an enclosed and small space and then ignite it, you will get a release of expanding gas that is extremely high in energy. Through history, humans have learned how to create a cycle that allows us to set off that type of explosion hundreds and hundreds of times within a single minute. We then learned how to efficiently harness that incredible amount of energy and use it to our own advantage. This gave birth to one of the greatest inventions in human history, which is the core of the car engine. The figure at the bottom right shows two of the most well-known internal combustion engines, which is the gas-powered and diesel-powered engines. These are obviously both internal combustion, but there are some distinct differences between the two. The diesel engine, which was created by Rudolf Diesel, who I had previously mentioned earlier, uses diesel fuel, which is higher in energy content. Rudolf theorized to many that higher compression leads to a higher efficiency and more power. When the piston squeezes air with the cylinder, the air inside becomes very concentrated, and since it uses diesel, which possesses a higher energy content, the likelihood of the fuel reacting with the concentrated air is greater. Another way to think of it is when air molecules are packed so close together, fuel has a better chance of reacting with as many oxygen molecules as possible. It turns out that what Rudolf theorized was exactly right, as the compression ratio of diesel is much higher than gasoline. A diesel engine gets better mileage than gas, but the trade-off is the price of diesel is normally a lot more expensive than gas. When comparing the engines, you can look at the gas-powered engine as a sort of racehorse that's fiery, fast, and high-strung, while the diesel is like a workhorse that's slower, but a lot stronger and can endure a lot more. History to present day. Various scientists and engineers have contributed to the development of the basic engine, dating all the way back to 1509, where Leonardo da Vinci described the idea of a compressionless engine. We don't see the revolutionary spark ignition 4-cycle internal combustion engine until 1876. This revolutionary engine is brought onto the scene by German engineer Nicholas Otto. In 1879, Carl Benz, who we now know of the Mercedes-Benz car dealership, was working independently and was granted a patent for his internal combustion engine, a reliable 2-stroke gas engine based on Nicholas Otto's design of the 4-stroke. Later, Benz designs and built his own 4-stroke engine that was used in his automobiles, which became the first automobiles in production. And then in 1892, we see the creation of the compression ignition engine by Rudolf Diesel, which finally gets patented in 1893. As new technologies become available and the demand for new and better engines arises, we see dramatic increases in the complexity and knowledge of engines. Many of these scientists and engineers had no idea what their inventions would eventually give birth to, such as space travel and being able to travel across the planet in only a matter of hours. In 1926, Robert Goddard created the very first liquid-fueled rocket. 13 years later, in 1939, the Heinkel HE-178, which name I probably just butchered, became the world's first jet aircraft. Internal combustion engine parts and their purposes. There are many parts to an internal combustion engine, but these are some of the most important. I will briefly explain each one's function that I've listed above. The cylinder and cylinder head. The cylinder is the part in which the intake of fuel, compression of fuel, and burning of fuel all take place. It is essentially the main part of an internal combustion engine. The main function of the cylinder is to guide the piston. It is in direct contact with the products of combustion, so it must be cooled. To help with cooling, the cylinder has a water jacket that is situated on the outer side of the cylinder. At the upper end of the cylinder sits the cylinder head, which is the picture on the right, and at the bottom end the crankcase is bolted on. I'll talk about the crankcase later. The upper side of the cylinder is a combustion chamber where fuel burns. To handle all this pressure and temperature generated by combustion of the fuel, the cylinder material should have a high compressive strength, so it is normally made by high-grade cast iron. The main function of the cylinder head is to seal the cylinder block and to prevent any gases from entering and leaving. The piston and piston rings. A piston is basically a sliding shaft that fits inside the cylinder. Its purpose is to change the volume enclosed by the cylinder to exert a force on a fluid inside the cylinder. In an engine, its purpose is to transfer force from expanding gas in the cylinder to the crankshaft via a piston rod or connecting rod, which I'll talk about here in a second. It's normally made out of aluminum alloy and sometimes cast iron. The piston rings have a handful of purposes, which makes them very important. They provide good sealing between the piston and engine cylinder. They regulate the amount of lubricant into the engine cylinder and provide proper lubrication. They also transfer heat from the piston through the engine wall and fins and minimize friction between the piston and the engine wall. Connecting rod and crankshaft. A connecting rod transfers motion from the piston to the crankshaft and functions as a sort of lever arm. Connecting rods are commonly made from cast aluminum alloy and are designed to withstand dynamic stresses from combustion and piston movement. The crankshaft. The main function of the crankshaft is to translate the linear reciprocating motion of a piston into the rotational motion required by the vehicle. The engine bearings and crankcase. Everywhere there is a rotary action in the engine, these bearings are needed. Bearings are used to support the moving parts. The main function of bearings is to reduce friction between these moving parts. And the crankcase is basically just a covering that encloses the crankshaft that I talked about earlier. Valves and spark plugs. Valves permit the intake of fuel and air, and then they must seal that compression. After the small explosion, the exhaust valve will allow the burned gases to leave the combustion chamber. The spark plug's main function is to ignite the air and fuel mixture by delivering a small electric spark. Injector and flywheel. The fuel injectors spray a fine gasoline or diesel mist, depending on the engine, into the engine's intake manifold, which then delivers it to the engine for combustion with the oxygen that the engine is receiving. This mist makes for more efficient burning of the gas and combustion than if it were in some sort of droplet form. The flywheel is a device that is specifically designed to efficiently store rotational energy. It's secured onto the crankshaft, and its main function is to rotate the shaft during the preparatory stroke. It also makes crankshaft rotation more uniform. The future of these engines. Due to rising greenhouse gases from the burning of fossil fuels, scientists and engineers have looked to designing electric cars. CEO of Nissan, Carlos Ghosn, whose name I also butchered, I'm sure, has estimated that nearly 10% of global new car sales in 2020 will be for electric, battery-powered vehicles. Nissan plans on introducing at least 4 new electric cars within the next couple years. Some estimate that the percentage will be lower because of the fact that these battery-powered vehicles are so expensive. In some models, the battery alone can cost you over $20,000. but this still leaves internal combustion engines as 90% of global car sales. Internal combustion engines, the use of them may drop significantly in the future as federal fuel economy standards increase dramatically, but it's projected that we will always have these types of engines around. We can never be too certain on what the future may hold. Thank you for listening to my presentation.